There are three chief algebraic methods for solving a system of equations with two variables, and those three methods are the substitution method, the elimination method, and the graphical method. Now you might be remembering that we studied lines before, and when we studied lines before, we were using the standard form y equals mx plus b, the slope-intercept form, because we were interested in graphing those lines and talking about their slope and their y-intercept and their x-intercept. Now, in systems of equations, it's helpful to express equations in a different standard form. So the standard form we use for systems of equations has the x and y terms on one side and a constant on the other. And so we have the form ax plus by is equal to c. It's still a line, it still has a slope of whatever you figure out and a y-intercept of whatever you figure it out to be. We just are putting it into a different form. And if you have two such equations or two such lines, then the form, the standard form, will be two equations, and so I've indicated that by using little subscripts to differentiate between the two different lines. Now, since these are equations for two lines, we have certain situations that may arise. For example, two lines may or may not intersect. A solution is the intersection point of the two lines, so if the lines don't intersect, there may not be a solution. A third possibility is that these equations may actually describe the same exact set of points, so there may be infinitely many solutions. And we'll talk more about this later, but now I want to show you one example of each of the three types of methods of solving these linear equations, these systems of linear equations. In the first method, the graphical method, I'll just set up for you, and I'll let you graph and, well, maybe we'll work it out. Let's see what we do. With the graphical method, we want to re-express the equations in the familiar slope-intercept form, because that's how we most easily graph. You could also do the 3 points method, the table method, and find the y-intercept and the x-intercept in the third point. But let's recall how we do the y equals mx plus b form. So this first equation would become y equals negative 2x minus 1. And the second equation would become, let's see if I can do this right really quick here. It's going to be negative 1/2 x, and it's going to be plus 4. I think I did that right because I'm going to subtract x and then divide by 2. So that, or divide by negative 2. So that seems okay. Now I have the equations in slope-intercept form, so I can sketch the graph. So let's see what we get here. I'll give it a try. So y-axis, x-axis. The first one has a slope of negative 2 and a y-intercept of negative 1. So if this is where negative 1 is, and we have a slope of negative 2, that means if we go up 2 units and then to the left 1 unit, up to, we will be at this point. That's going to be 1, and that's going to be negative 1. So if we go up 2 and to the left 1, we started here at the y-intercept, and we end up over here. And so now we can sketch that line using the slope-intercept form. The second one, y equals negative 1/2 x plus 4, has a y-intercept of 4. So I'll go up to 4, 2, 3, 4. So the y-intercept for the second equation, the second line, is 4. And the slope is negative 1/2. So if I go down 1 unit and to the left, no, to the right 2 units, so I have to go to the right 2 units. So I have to go 1, 2. All right, so if I go down 1 unit and to the left 2 units, I'll end up here, approximately right there. So now I can sketch that line. I'll try to get it. And you can see that at some point, I'll get this one going on here better. At some point, those two lines do have a common intersection point. You can see it right there. So if you do this carefully on some graph paper, well scaled, you should be able to determine the coordinates of those 2 points, or the 2 coordinates of that point. Okay, so the graphical method is okay, but you can see that you don't always get accurate or precise solutions. By the way, you could also do this in the TI calculator. So you could enter these into 2 of your y functions and use the calc intersect or intersection on your calculator. So you could also do it that way. But this graphical method is not always precise, and so we want to have an algebraic method for solving these systems of equations. And so the first algebraic method is the method of substitution. So sometimes the equation or one of the equations that you're given is easily solved for one of the variables. For example, in this next system of equations, the first equation, x minus y equals 1, is easily solved for x. You just add y to both sides, and this equation becomes x equals 1 plus y. Well, now you can substitute this value of x into the second equation wherever you see the variable x. So in the second equation, we will put 4 times 1 plus y plus 3y equals 18. And so now it just is a matter of solving this equation for y. So I'll let you fill out those details. Solve this equation for y. And then after you've gotten or obtained the value of y, substitute that value of y into the equation here to figure out what x is. Then check by substituting the ordered pair into both of the original equations. That's the final method or the final opportunity to determine if you've made an error. So if you find that you check and the check doesn't work, then start looking for some sort of error in your solution process. The third method that we'll study is the elimination method. Now, sometimes the equations are given in such a way that it's not convenient to solve for one of the variables, and so we use the elimination method. And the elimination method requires that in the two equations for one of the variables, the coefficients are opposites. And this requirement is because when we use the elimination method, we eliminate a variable by adding the two equations together. So you see, for example, in this example here, adding those two equations together would not eliminate a variable. We would get 5x plus 2y equals 19. So we still have two variables. But in this system of equations, if we add these two equations together, we get 4x equals 8, which we can solve and get x equals 2. And now that you know what x is, you can substitute the value of x into this equation to calculate y. And then as your check, you would substitute both of the values into this equation to verify that you have indeed found the ordered pair solution. The only tricky thing with the elimination method is, of course, in this particular system, the coefficients were already given as opposites. So sometimes you just have to multiply one equation by some number to get the coefficients to be opposite. So, for example, if you look at this example, the graphical method example, you could multiply this first equation by positive 2. If you multiply every term in that first equation by positive 2, you would get 4x plus 2y equals negative 1. The second equation is x minus 2y equals negative 8. So you can see now you have opposite coefficients for the variable y, so you can add the equations together and that will eliminate a variable. So you get 5x equals negative 9, and so x equals negative 9/5. So it looks like the solution for that graphical method problem is not very nice. At any rate, that's how the elimination method works. So with systems of equations, you have, of course, one of three possible outcomes. Either the lines whose equations you are given, either they intersect at a single point, in which case the system has exactly one solution, or the two lines are parallel, and so the system doesn't have a solution at all, or the two equations are actually equations for the same line. The lines coincide. The equations are for the same line, and in that case the system has infinitely many solutions. So it's nice to have some examples of those types. So let's study these two systems of equations and see what happens in those other cases where the lines are either parallel or they coincide. So this first system of equations, x plus 4y equals 8 and 3x plus 12y equals 2, I'm going to solve by the elimination method. Actually, no, I'm going to solve that one by the substitution method. The first equation is easily solved for x. The first equation gives us that x equals 8 minus 4y. So I substitute that value of x into the second equation, there, where I see x, and I will end up with 3 times 8 minus 4y, plus 12y is equal to 2. So we'll just work this out. 3 times 8 is 24, minus 3 times 4 is 12y, plus 12y is equal to 2. Well, I see what's going to happen here. Minus 12y and plus 12y add up to 0, so I end up with the false statement, 24 equals 2. So the first thing I think is, did I make a mistake? So I go back and check through my work and look for a mistake, and I don't see any mistakes. Therefore, I know I didn't make a mistake. And so my conclusion is that this is not true. Therefore, there must not be an intersection point. Therefore, these lines must be parallel. Let's put them into the slope-intercept form. The first one in the slope-intercept form would be y equals negative 1/4 x. 8 divided by 4 is 2, plus 2. So this line has slope negative 1/4. The second one we would end up with, let's do this in a couple of steps. 12y equals negative 3x plus 2. So we divide by 12, and y equals negative 1/4 x plus 1/6, and so you see the two lines do have the same slope, and they're parallel, and that's why you obtained this contradiction. So when you obtain a contradiction, that means you know that there is no solution because the lines are parallel. So say parallel lines. No solution, parallel lines. That's the answer. Okay, so that's what happens when the lines are parallel. Now the next example will show us what happens when the equations are actually two equations for the same line. So we have 2x minus 6y equals 10, and negative 3x plus 9y equals negative 15. So let's multiply the first equation by 3 to give us 6x for the coefficient, or 6 for the coefficient of x, and we'll multiply the second equation by 2 to give us negative 6 for the coefficient of x, and then we'll add together and have the x terms adding each other out. So 3 times 2x would give us 6x, and 3 times 6y will be a negative 18y, and then we multiply by 3 on, don't forget, multiply by 3 on both sides equals 30. Now for the second equation, we get 2 times negative 3x, negative 6x, 2 times 9y plus 18y equals, this is a y, equals 2 times negative 15, negative 30. This is looking very suspicious. The x's add up to 0, the y's add up to 0, so on the left-hand side I get 0. What do I get on the right-hand side? Well, these two numbers add up to 0, so I get 0 equals 0. That is a true statement. I got a true statement, and so that means that every ordered pair that satisfies this equation also satisfies that equation, and in other words, these are actually two equations for the same line. And you can see that actually right here. All you have to do is multiply the second one by negative 1, and you can see that it's exactly the same equation as the first one. As soon as you see that, you can just say, these lines coincide. Lines coincide. C-O-I-N-C-I-D-E. Lines coincide. Okay, now when the lines coincide, we like to take it one step further, just one step further, and specify what the solutions look like. But we can't list the solutions, but we can write a formula for the solutions. So for example, if you want to write the solutions in terms of x, then we would simply say that the x values can be any number. Let's say the x value can be any number. Let's call it s. And if x is s, what's y? Well, since these are two equations for the same line, it doesn't matter which one we use. We'll substitute s for x. 2s minus 6y equals 10, and now we'll solve for y. So we get minus 6y equals negative 2s plus 10. And continuing to solve for y, we'll now divide by negative 6, and so we get y equals 1/3 s plus, or actually minus, because it's it's minus because I'm going to divide by -6, so minus 5/3. So what we have here is we don't have individual single numbers, but we do know that if we know a value for x, whatever that is, and we're using the different letter s, then our y value is 1/3 s minus 5/3. Oops, 5/3. I was thinking of t. I was thinking of t because usually we use the letter t. I don't know why I picked s here. At any rate, so if you pick a value for s, you can find a value for y. So you can find an infinite number of ordered pairs. In fact, you can find 3 ordered pairs that solve this system if you like. You can find the x-intercept, you can find the y-intercept. There's all sorts of interesting things you can do. Okay, so you'll see that stuff in your homework problems if you decide to do any for this section. So the next couple of problems are word problems that lead to systems of equations. So the first one has to do with a distance problem. So let's read the problem. A man flies a small airplane from Fargo to Bismarck, North Dakota, a distance of 180 miles. Because he is flying into a headwind, the trip takes him 2 hours. On the way back, the wind is still blowing at the same speed, so the return trip only takes 1 hour and 12 minutes. What is his speed in still air, and how fast is the wind blowing? So you can see that being able to solve a problem like this is important for, air traffic controllers and pilots, and, pilots who fly small planes, large planes, doesn't really matter. So here's an actual, useful thing about being able to solve a system of equations, and in particular being able to solve a distance, rate, and time problem. Now, I like to solve distance, rate, and time problems by using a table. So I set up a table, and I set it up, and I know that I have 2 trips, so there are going to be 2 rows, and I know I have, for the 2 trips, one of them is going with the wind, and one of them is going against the wind. So I can also differentiate between the 2 trips by saying whether they're from Bismarck to Fargo or Fargo to Bismarck. So let's look at the first one, which is Fargo to Bismarck. So we're going from Fargo to Bismarck. And we're told what that distance is. We're told that that distance is 180 miles. I'm going to put 180 miles. Okay. Now distance equals rate times time. I'm going to have to fill in this whole table if I can. Well, certainly if the distance from Fargo to Bismarck is 180 miles, I can fill in that the distance from Bismarck to Fargo is 180 miles. So I may as well put that in there right now. Okay. I'm also told what the times are. Okay, so here when he's flying into the headwind, and that's from Fargo to Bismarck. The trip takes him 2 hours. That's my time, so I'll put 2 hours right here. That's the time for this trip. Now the other trip takes 1 hour and 12 minutes, okay? So you have to know what part of an hour is 12 minutes. 12 minutes is 1/5 of an hour, so it's 1 hour plus 1/5 of an hour. You can figure that out. And that is 6/5 of an hour. I don't like to use decimals, I like to use fractions. That's just the way I am, so we'll just use 6/5 hours, so it's 1 1/5 hour. Now we need the rates. Well, what do we know about the rates? Well, we know that he is flying the plane's flying at some speed, which we don't know, and we know that the wind is blowing at some speed, which we don't know, but we do know that when he's blowing with the wind, it adds to his speed, and when he's blowing again, or when he's flying against the wind, it takes away from his speed. So let's let S equal the speed of the wind. That's the speed of the wind. Okay. Speed of the wind, and we will let's let R be the speed of the plane. When we say the speed of the plane, we mean the speed of the plane in still air, like with no wind, without the wind. Okay, so if S is the speed of the wind and R is the speed of the plane, surely R is greater than S. We know that. If it's not, then you can't fly the plane. So R has to be greater than S, and so we know that if we take R and subtract S, that's how fast he's going when he's going against the wind, which is Fargo to Bismarck. So in the rate for Fargo to Bismarck, I can put R minus S. On the other hand, when he's flying with the wind from Bismarck to Fargo, the wind is adding to his speed, so he gets to fly at the speed of r plus s. It takes him less time. Well, now it's pretty much set up, and I'm going to let you finish the solving of this. We know that distance is equal to rate times time, and so we have two equations that we can write. The first equation is that 180 equals r minus s times 2, and the second equation we can write is 180 equals r plus s times 6 over 5. So, you can solve that system of equations quite simply. You just, simplify things and either use elimination or substitution method, and you should be able to come up with the solution. I worked this one a while ago, and I think, if I'm not mistaken, that the answers were, I don't even want to guess because I could be wrong. I don't want to steer you wrong. So just work those, and if you want to ask about them, you can always leave a message. The second problem deals with nutrition. A researcher performs an experiment to test a hypothesis that involves the nutrients niacin and retinol. She feeds one group of laboratory rats a daily diet of precisely 32 units of niacin and 22,000 units of retinol. She uses two types of commercial pellet foods. Food A contains 0.12 units of niacin and 100 units of retinol per gram. Food B contains 0.20 unit of niacin and 50 units of retinol per gram. And the question is, how many grams of each food does she need, or does she feed this group of rats each day? How many grams of each food? Okay. So we're looking for the number of grams of each food, and so we have food A and we have food B. So why don't we let little letter A equal the number of grams of food A per day, and we'll let little letter B equal the number of grams of food B per day. You could use X and Y if you want, but then you have to remember which one is X and which one is Y. So I just use the small letters that go with the big letters, and then I know very easily which is which. Okay, so we know how many grams is what we're looking for. And what do we know about these two foods? Well, let's set the information up in a table because it's really confusing when it's written in words like that. So we have one row for food A and another row for food B. Okay, so we have food A and food B. We know that she needs niacin and retinol, so we should have two columns, one for niacin, which I'll use N, and one for retinol, which I'll just indicate with R. Okay, so now we have our table. We can put our information in here. Now, what are we given in the problem? She has to give the rats precisely 32 units of niacin and 22,000 units of retinol. That's the total amount that she gets from feeding the rats these two types of food. So we need one more row, and that row is the total row, because we know that the total amount of niacin is 32 units, and we know that the total amount of retinol is 22,000 units. So that goes there. Remember, the rats get this niacin and retinol by eating foods A and B. What do we know about those two foods? Food A contains 0.12 units of niacin. So right here we could put 0.12 units, because that's the amount of niacin in food A. Food B contains 0.20 units of niacin. So in the food B column for niacin, we can put 0.2 units. For the retinol, food A contains, let's see, where is it? 100 units of retinol. So there's a 100 right here. And food B contains, 50 units of retinol, 50 units. Now these are units per gram. Let me write that, per gram. Units per gram. Units per gram and units per gram. Well, that's why these numbers don't add up to 32 and 22,000, because those are the number of units per gram. So you have to figure out how many grams they get. Remember that. So actually now we can see how our equations are going to work out, because we know that the amount of niacin in food A, that many units per gram times that many grams, plus the amount of niacin in food B, that many units per gram times that many grams, should equal 32. So let's write that down. I guess we can't see the variable. There it is. Okay. So the amount of niacin in food A can be found by taking the 0.12 units per gram and multiplying that times A, which is the number of grams, so that the grams will cancel out. See that? And we end up with 0.12 units of A. So we'll just write 0.12 of A. Now for the B, we can do the same thing. For the B, we have 0.2 units per gram, 0.2 units per gram, but we're using B for our number of grams of food B. So again, the units B for grams cancel out and you get 0.2 of B. So add to that 0.2 of B, and that should equal 32. Now we'll do the same thing for the retinol. So we have 100 units per gram in food A, so A grams, plus 50 units per gram in food B, so that's going to be B grams, should equal 22,000. 22,000. Now the numbers are kind of big here, but here you have a system of equations which is quite easily solved. In fact, if you wait until you see how to solve a system of equations using matrices with your TI graphing calculator, you could solve this on your TI calculator. Otherwise, if you want to just play around with it and try to solve it by either the substitution or elimination method, feel free to do that.